So I can actually start with the formal welcoming the resource person, Dr. Himlata Maheshwari. Uh, she has been very kind to agree to our consent and deliver this lecture at the evening session. And I know that because she is working also, so this must be a taxing job after an entire day work. Again, sitting down in front of a computer and delivering a lecture with demos, of course, will be taxing. But I would like to thank you and appreciate your commitment and agreeing to our request that you have agreed and you are over here on before time rather to engage this session under the Atal FDP scheme, in which we have got uh, PG students as well as uh, people from teaching faculty, mostly from engineering, computer science background, but some from other fields as well, like mathematics and statistics. So, I would like to introduce the speaker of the evening today. She has actually completed the PhD in signal processing from IIT Delhi in 2015 and currently working as a project leader DSP algorithm with Miami Technology Hyderabad since 2017. She has previously worked with Samsung R&D India, Cadence Design System, Symbiosis International University. Her research interest spans the area of acoustics, speech enhancement, microphone array processing. She has experience in the direction of arrival estimation, source separation, and spatial audio. So all these things are very much relevant to our basic theme of speech-enabled automation technologies. And she is over here to conduct the session on speech enhancement techniques for automation, and there will be some demos as well. And that's why we had passed on the request from the resource person that everybody should have a headphone that will be useful there, and it will be helpful for you to appreciate the techniques that will be, because it will be audio, so it will be much more better. uh, I would also like to thank Atal FDP for this particular sanctioning this particular program, which is based on the automation and use of speech in automation. This is the first week of online lecturing. With this word, I would open the floor and leave you with Dr. Hemlata Maheshwari, and she will, from here onwards, engage that session. We do have 50 minutes of first section, you can say, followed by maybe a break and question and answer, and then again 50 minutes. So it depends upon your own choice if you want to have questions in between. Otherwise, the participants will enter the questions in the chat box, and after 50 minutes or whatever time you feel suitable that you have finished a section, we can have those question and answer session. So it is a choice of your own. Okay. With this word, I leave the floor to you. Please.
Sure. Okay. Yeah, thank you so much, sir, for giving me this opportunity. It's honor to be here. And I think this presentation will be of some help to all the participants. So thank you again. Yeah, so I'll share my screen. I think audio sharing I need to verify, but okay, at the time of demo we can check again if there's a problem. So we can start with the PPT. Yes. So yeah. So as sir has mentioned, I am presently working with Miami Technologies. My name is Hemlata Maheshwari. So I have a background in acoustics and especially DSP algorithms. So I will try to give a brief introduction, what work we do, and in general, what is the work which audio industry demands, and what is my experience with respect to the DSP algorithms. So here we have a project outline. I have tried to cover three algorithms. I have worked on a lot of algorithms, but majorly my primary contribution has been in the area of spatial audio, source separation, and time delay estimation. So these three algorithms I will try to cover. Before that, I will try to give an introduction of speech enhancement. So in the next slide, if we see here in bottom left, we have some devices like this is Echo Dot, and similarly we have ASR connected devices from Microsoft, and similarly we have OK Google from Google. This is Alexa based Echo Dot. We have mobile phones also. We have smart speakers, and we have smart watches and mobile telephone lines. So in general, we can say there are two categories. One is voice calling, and secondly any voice enabled device. So one in voice enabled device, our voices are used for command and control, to control, and ultimately our voice is going for command recognition by an ASR system, automatic speech recognition system. And based on ASR we have some assistants. It's similar to Alexa voice service or OK Google, for example. While in case of a telephone, we have voice calling. So what happens is, in presence of noise, normally when we are giving commands to these devices, and these will be recognized, but in a household environment, especially when we have work from home, we have some kitchen noise, TV noise, for example. So we want our commands or voices.
Excuse me, slides are not changing. Are you changing slides?
No, as of now, this is slide
Oh,
number 6.
no,
Sorry,
no, no.
second.
Actually, it's on the first slide only. Maybe
First,
you can unshare then share again.
okay, one second. I'll try again. Okay, one second. Now is it changing?
Yeah, now it is changing. Now it's changing.
Okay, no problem. We'll start over again. Okay, so this is the presentation outline. I have primarily worked in these three algorithms, as I just mentioned. First is spatial audio, then source separation, and time delay estimation. So, spatial audio, source separation, and time delay estimation, these come mainly under speech enhancement related work only. So in this left figure, if we see, we have an Echo Dot device here, Alexa based Echo Dot. We have similar products, voice assistants from Google, where we use OK Google and Microsoft. We have smartphones. Here we have a smart speaker, a smartwatch, and landline phone. So in general, categories, voice calling, where we only voice to voice communication is there, and in these ASR based device, where we have at the end we do not have a human listener. Here we are calling to a cloud based ASR system. So in ASR system, for example, Alexa voice service is using ASR for to give us a virtual assistant. So in this voice control devices, we actually do command and control. So what happens in case of background noise like kitchen noise or TV noise is there, what it becomes difficult for the ASR system to recognize the command. So our purpose is to enhance the voice. Similarly, in voice calling also, when we have work from home setup, or in teleconferencing when we have multiple speakers, we want to enhance the voice which is going to the end user. Similarly in smart speakers and Echo Dot. So in general, we can say as of currently in industry, there is a lot of product range which are called IoT devices, and then which use the voice. So whenever we have at the end we have a ASR device, the speech recognition system will assume that the voice is clean. So before passing the speech or voice to the speech recognition system, we need to do speech enhancement. And so it will be in general useful for voice calling, teleconferencing, or enabled devices. But mostly ASR systems are very much sensitive to background noise. Human listeners still can interpret. So my current employer, Miami Technologies, it's a media processing and real-time communication group. It primarily works in the field of voice-based solutions, providing voice-based solutions depending on the requirement of the IoT devices. We do have solutions for voice calling as well as ASR systems also. So This is a simple example. It's a very simple example of a schematic echo dot device. Here we have a microphone array, and this person, let us say the owner, wants to say something. Alexa, add this to the to-do list. Now here we have some people talking in the background. Here we have a fan noise, and here we have a loudspeaker in the Alexa device. Let us say some music is playing here. And this is a loudspeaker inbuilt into the Echo Dot device. So if I have a music coming here or competing sources or noise, and here we have some other noise from surrounding directions, and whatever commands are going to my network cloud here, it needs a clean wake word signal to be processed by the cloud. Now these all these things, when we are saying, as I again said, there are two parts. We can divide, create a line here. So this part, when which takes care of cleaning up the signal, we call it as front end signal processing. And this part, like we can say, the speech based signal processing. So I am primarily working in signal processing for speech enhancement. We also have different signal processing for speech recognition. So here we have some beamformer or clean voice processing for this, or echo cancellation here, where we have noise reduction. So this is the overall idea. So if we are working with any type of automatic device, we can roughly, for our understanding, it's not a strict term. We can roughly divide it into two parts. So here in the next slide, we have in front end signal processing and back end. So when we are talking about speech recognition, speech to text conversion or voice transformation, in our mobile phone, we have speaker identification or speaker verification. All this is related to speech signal processing. But when it comes to cleaning the speech and doing speech enhancement or voice enhancement, we have these techniques. So we employ echo cancellation, noise suppression, interference cancellation, beamforming, and this all comes under acoustical signal processing. In industry, again, we'll use speech signal processing only, but in our movie, we have acoustics part here more involved here, and speech part more involved here. So here we'll come to the first algorithm related to speech enhancement. First algorithm which I'll be covering is spatial audio. So what is a spatial audio? So this term is coming from space, actually, space properties. So this is also referred as a virtual acoustic environment. Another common name, or we can say in literature, in academics, spatial audio is also mentioned as virtual acoustic environment or 3D audio. So we'll try to understand this. We all must have used and encountered spatial audio, and we all must have when I play this movie in a movie theater, I want the user or listener to have the same experience of the movie scene, that the sounds should be coming from all the direction. So for audio, the special information we try to preserve and give the user the impact, or we can say that basically the experience of a space and the situation of the various sound sources in space has to be conveyed to the end user. So that type of we can say mechanism is called spatial audio, and we this is a very simplified example. So now if we look at the techniques how it is conventionally done. So one of the technique for spatial audio is simply, as in our home we have a surround sound system. In surround sound system we have a listeners here. We have, let us say, we have a movie on a TV. We have a 7.1 or 5.1, any type of speakers. So in surround sound, the user is situated with a set of speakers around him. And if my original media content is supported by spatial audio, the recordings would be done in automatically in the respective manner. So to simulate the 3D sound effect, sound is played with different loudness or out of phase or at slightly different times from each speaker. So basically, while recording the scene, we try to preserve the information using different mics, different setups that comes in audio engineering. And while playing back, we take care that the same placement is used. So this has to come from the channel. For example, Netflix now supports this system. In a movie theater, if we go, in movie theater, we all are familiar. We have different speakers and the sound will be played accordingly. Now here we have some limitations because complete 360-degree coverage is not possible here, but still as the number of speakers increase in a movie theater or in a home also, we get good ambience, and we get some impression of sound. So surround sound system is one of the technique for special audio. There are many techniques, so we are trying to just check the introduction part. So surround sound is the most simplest and one of the most commonly used setup in entertainment industry. It comes in a variety of speaker placement setups. Recently there is another technology which is more commonly used, which is head related transfer function based, and we'll be covering that technology here. So what is the difference with respect to surround sound and HRTF based, we'll see. So this surround sound system, basically we are recording in a required format. At the time of recording, we are recording the scene with the help of microphones and playing. So when it comes to digital signal processing, HRTF is more of a DSP based technique where recording could be done in any manner, but still we can have the playback of sound with special information. So here we'll come to the formal definition of virtual acoustic environment, spatial audio, 3D audio. Why we are using the term virtual is because originally the sound was not recorded like that. So virtual acoustic environment, I think there's some spelling mistake, I'm sorry for that. Virtual acoustic environment refers to digitally manipulating sound such that the desired space property is conveyed to the listener. How we do that is, for if we assume this is a 3D diagram, we have a microphone array here, we have a sound source here. So when our sound source emits sound waves and we have microphone arrays here, so the sound waves or the signal recorded by each of the microphone definitely will be a function of theta and phi, and this is the distance r. So whatever we are observing at the microphone array will have some attributes, and those attributes are called sound specialization cues. So what happens is the amplitude energy level which is recorded at this microphone array relative the time difference, sound will arrive at different times here. So whatever the waves we are recording, and their properties will definitely be impacted by the position of the sound source. So if we can utilize whatever the properties which are varying with the position of sound source, those we call as the specialization cues, like time difference, energy level difference, these are the cues. And if we can utilize that information and digitally tweak the signal, we can somehow convey the properties of sound source to the user. So that process of manipulating sound that we are referring as a 3D audio. This is a simple example. It's a very simplified diagram. We can magnify this particular case and see it for a. If I have a 3 microphone array, mic number 1, 2, 3, and I have a sound source here. So this first mic is the farthest from sound. The distance is maximum here, R1. So for this particular mic, my amplitude will be smallest and it will appear latest. The time arrival will be more. So here the amplitude and time delay of arrival. So my signal will be arriving latest and the amplitude will be small. Similarly for mic number 2 here and mic number 3 here. So what we are seeing here is simply time delay of the signals recorded by microphones and their amplitudes. Both are impacted definitely because of this relative position. So there's a simple equation. We need not to go into detail. Whatever we have sound source here, mic number 1 will record a modified version of this signal and some noise. Similarly for all of this. So now if we can record this x1, x2 and x3, and with this we can preserve this information of time delay and energy difference, we can somehow convey the relative difference. So what we are trying to say here is these are two elementary. Time delay and amplitude are two elementary cues for specialization of sound source with respect to the microphone array. And when these two microphones, rather than if we replace these microphones, if we have a human listener here, so in place of microphones we have the human ears, right? So here we'll have the term oral. For humans we use this term interoral time delay, interoral level difference. Similarly, the structure, outer ear structure of the human will have a response which can be represented in terms of a transfer function, just like a filter. It is called the pinna response. Similarly, we have shoulder reverberation impacts also. So all these for humans, When we represent this information, the localization attributes we preserve in form of a database, and when we can use it later. So, okay, so here we have a sound source here, we have a human listener here, and we have a left ear. So, for this particular ear, the difference of the travel path from sound source to the left ear, we are trying to represent that as a filter and a transfer function. So, it is called a head related transfer function for left ear. Similarly, head related transfer function for right ear. So, this is the direct path, and we are trying to modulate the complete. Characteristic of the human ear, the body structure, the travel path, everything we are trying to store in form of a filter. And these filters are digital filters, they are stored in database. So head related transfer function, the formal definition is it is a response that characterizes how an ear receives a sound from a point in space. So when we the difference of the travel path or the difference of sound source versus the human ear, the complete characteristic we are trying to store in the form of a filter, and that is called HRTF. And this filter, if we have in our system, we can digitally tweak any type of sound to give the illusion of the sound source. So how it is done is, for a human listener in a laboratory, we use microphones inside the ear canal. Tiny microphones are placed inside the human ear. For example, then I will use a standard procedure in a lab. We have a sound source, and what we'll do is we will transmit some standard sound across all the different positions in the lab, what different angles, different distances, and different r, theta, and phi positions. For all of those, the microphones will record sound from within the ear of a person or model. Differences between the original sound and recordings are used to create filters. These filters are later applied at the time of sound reproduction. They are applied to generate sounds to create the illusion of dimensions. So this is another diagram. So this we have already seen. So this is a front view for recording HRTF, and this is the side view. So this cross will denote one point. For example, this is a room. So this loudspeaker is placed at all these points across a grid points. Obviously, we cannot have infinite resolution. So for example, we move this loudspeaker by 10 degree each time, 20 degrees in the horizontal plane, and again in the vertical plane also we can make. So for certain resolution, we can make grid points, and from all the grid points we will transmit the sound using loudspeaker and record the HRTF. So basically, for this particular listener, for example, these cross points, as I said, are representing. So once we have this resolution, let us say at a distance of here, let us say distance of 1 meter, then similarly 2 meters or three, going up to 5 meters. So with a certain resolution of distance and angles in horizontal and vertical plane, we use the grid points to do the recordings using microphones, and then we calculate the difference between the original sound and the recorded sound, and we calculate the HRTF function points. So this is a general diagram. So let us say we make a database like this. We have a HRTF database at certain sampling rate. We need not to understand this whole diagram. We can just have a simplified overview. So we need not to go through the whole flow. For example, we have HRTF. So if I have an audio file now, we'll simply read the file, do resampling. So from here, suppose my required coordinates are, let us say, 10 degree or 20 degree in the space. What I'll do is basically I'll simply fetch my filters from this database, and these are for left and right ear. Here, even if I'm having a mono sound here, I have two left and right ear filters. I'll simply do the convolution here and generate an output file. So this file could be again stereo, definitely, if it is for left. And so when we hear it through earphones, it should give us the impact of a stereo. And another thing here is if our object is indoors, because obviously we are if we are doing recording in an anechoic chamber for HRTF database, then in that case the reverberation impact will not come. So we have another mechanism here. We, to represent the room and reverberation, we use IR filters. This if the object is outdoors, we can disable this. If the object is inside a room, we can enable this. So basically, major part of direction is coming from our FIR filters, which are fresh from HRTF database. minor part for room reverberation is coming from IR filters. The way we have created the database for HRTF, we can also create the database for room reverberation using IR filters similarly, and we can simply do the resampling and downsampling for that. So in this now we can have as many sources as possible here, and we can generate the output by adding them. It can support almost all sampling rates and stereo channels also. So now we'll come to this part as the conclusion. So here this is the schematic diagram. We take a mono source, we take the image coordinates, we do HRTF database interpolation here, and then we give to the user left and right here. So so user will definitely perceive some location of image depending on this HRTF database. So now, as of now, it is coming. This particular feature is being supported by commercial earbuds. It definitely is there in Apple AirPods. It is there with Google earbuds also. Platforms like Netflix, in general, in TV or in mobiles also, we have a Netflix system, and we do not want to use the 7.1 or 5.1. So if we have a 7.1 system in Netflix supported media, and we want to use earphones rather than the 7.1 system, if we use the earphones, we still can perceive the same impact of the 7.1 or 5.1 system using the earphones. So now Netflix has supported this for both for Android and definitely Apple phones also. They are giving this support. Similarly, commercial earbuds. So just with the we need not to in fact buy a 7.1 system. Using headphones, we can use it. So this is one of the example of a special audio, and I have done very basically POC, or we can say simplified level work here for this demonstration. So I'll try to share the audio. If there's a problem, please inform me. I'll start it now. Is it audible? Can is it getting shared the audio?
Yes, yes, it is. Yeah.
1 second. Okay, so I'll request you all to put the earphones. I will need to use 1 second. I need to use a headset. Okay. 'll play the next file. This is the scene actually which we are having. I think there is a lag here. Should I reconnect? I am not able to hear it. Okay, I'll need some help here. I think I need to share the audio before it is going. Okay, the train sound is visible. I'm trying to create a train sound, mono, and then stereo signal. Second one, can you hear that?
No, it is not audible actually.
Okay,
It is not
actually,
audible.
okay. I'm also hearing your voice after a long time only. I think some mistake I did in sharing the audio. Just give me a minute. I'll try
Yeah,
to.
yeah, sure.
Mm, I think I need to share the audio before joining the meeting. Just 1 second.
कैसा करूँ अच्छे लगा ठीक है सामने नाम कैसा वो सामने था दिखा निकल गई अरे अरे मैं ना तारीफ करवाने नहीं देती का तो फोन ना साइलेंट था सॉरी नहीं नहीं यार मैं तालीम में ही थी अभी आई हूँ मैं चलो बस मिल गई अच्छा चलो यार खैरियत से पहुंचो हम है ना इंशाल्लाह ट्रेन ट्रेन पे बैठ जाना तो मैसेज कर देना ठीक है चलो खैरियत से अरे भैया क्यों ये बहुत गलत बात है सही है चलो नुमाइश कैसी रही अच्छा नहीं नहीं हम लोग शाम कल मेरी बहन आ रही है ना तो हमसे तो कल शाम में जाएंगे रात में हम्म, हाँ
I'm getting this message. What I'll do is I'm directly playing through the folder. After that, I will start presenting because it is not allowing me to present both the things at the same time. Okay, so I'm really sorry for this.
नहीं ऐसा कुछ भी नहीं है यार चलो ठीक है दिया खैर से पहुंचो ठीक है मैसेज कर देना जब पहुंच जाओ ठीक है अस्सलाम वालेकुम
Wajid, am I audible here?
Yes, you are audible.
Actually, I'm getting a message due to the size of call. My mic is muted. So what I'll do is I'll play the audio first, then I will share my screen.
Yes, yes, fine. That's
Yeah, yeah. So I'm playing now again.
Yes.
Okay, second one I will play again. Okay. Is it okay? Is it tangible or not? I'm not sure. Should I play again?
yeah, both are audible. If you can play once more, so that
Okay, second, basically, this is the scene of a person standing on a platform. Train crosses from right to left. So, this first video is normal train sound. And second one, I'm playing now. Second, if we close the eyes, we should actually have the direction right to left, we should feel. So, I'm playing that now.
yeah, for some participants it may be from left to right, depending on how they have
Okay.
put their headset.
Okay. I think it's still because of network, some issue might be there. I will mail the files. We can listen. No problem.
Yes, yes,
It's not
fine, fine.
acceptable. Okay, I'll present again the screen now. Okay, we'll start from here. So these two files I'll be made basically mono signal we took for this train from internet and we did manipulate it and we generated a stereo signal. I'll mail the files if it is not perceptible, no problem. And your perception, it also depends if it is local file and over the internet, that difference is there. Secondly, alertness also. The user has to be alert. So this is regarding the special audio. This is the work which we are doing here. So these are the applications. First application, as I mentioned, is for a sound experience in 3D, like in movie theaters, cinemas, etc. In games, it has a very prominent application. If we are playing a video game on mobile phone, and we are trying to move the object, let us say a car sound or any type of object, as we are moving, scrolling through the screen, same coordinates we can connect and link to our app. So once we fetch the coordinates, that path or trajectory can be used, and again we can generate a HRTF based 3D sound which will come work. So here we need not to have any originally recorded sound. Here we are again, we can start this impact without having the actual stereo recording. In virtual reality applications, live performance, home theater, similar applications we are having. So this is one approach, the one which I am demonstrating, the special audio or HRTF based approach. This is the conventional DSP based approach. Recent trends is again in special audio, we are having machine learning and AI based algorithms also. Another approach is HR head related transfer function. When we have a head and we are putting microphones in the ear canals, we are basically using a person. So and the HRTF definitely, because it is head related transfer function. So the HRTF will be different for of a child, will be different than of a adult. So if a 12, 13-year-old gaming child has to have HRTF, we need to do customization. So recently there is a trend of individual or customized HRTF. For that, the trend is to, we have a standard HRTF database. We take picture of the ear of the child or any person, depending on the build of the person, the height and weight, everything. The distance between the ears will vary. So once the picture of the ear is taken, and some contour mapping and numerical methods are used to generate the head related transfer function of the person, and then we can provide a more personalized experience which is called as the individual or customized HRTF. So machine learning and AI based algorithms are also used to generate the head related transfer function. Here what we have done a special, like here we are seeing in this slide, if we go, this pure transmission of sound and then recording of this sound using microphones in the ears, this particular technique we are seeing, this is a DSP based algorithm. So recently there is also a trend of generating sound sources and HRTs, everything by machine learning or AI based methods. So here the main challenge with that will be, because this database, let us say for example, in the room we need 10-degree or 12-degree resolution, we need some distances also. So what this, but all the filters have to go into the system, let's say mobile phone, because as soon as the gamer or the user tries to enter a path, we need to fetch the corresponding HRTF from filter from the, I think I need to mute down 1 second. So once this HRTF is stored in the mobile, or let us say any type of device like tablet or something, the size or memory requirement of this DSB based HRTF, let us say I'm having grid points 20 by 20, 40, or maybe 100 grid points. And then each filter length is around 256 or 400 or 500. Those all the filters have to go into the database. But at the same time, if I go for a machine learning based database, filter length will increase, and that much memory we cannot consume in a mobile. So that is the drawback of MLAI based algorithms. But obviously, there are advantages also. So the main advantage of, like when we are talking about DSP based filters, we have simplicity here in the database. We have short length of filters, but obviously for individualized and customized HRTF, as I said, for from varying from person to person, we have good accuracy and we can have better representation in ML and AI based methods. But there the filter length will be large. So storing such length of filters could be a challenge, because over all the handheld devices will come with a finite memory, and it is not a good practice to load that much database. So these are the current algorithms applications as we are seeing here. So I will request, if you want to experience any I think Google phone latest, and more in near future many mobile phone will come. So if we are having Apple phone, definitely has Google phone also. So you can try enabling this special audio feature and try experiencing it for yourself. I will also definitely mail these audio files to Wajid. So we'll go back to the next topic. Before that, I think we can take up questions for this one.
Yeah, so there's a question here in the screen. Let me read for you. What is the role of pinna, and what will be the effect if the pinna size is small or large, especially if we talk with respect to kids and adult pinna?
Okay. Okay, I think I do not have a picture of ear pinna here. We can understand it using this way. So let us assume we are talking about this structure here. For this is a normal human head, let us say, and this is the outer. We all know that if we in the outer ear we have a funnel shaped structure. Outer ear consists of all the ridges and grooves. So it is sort of a parabolic reflector. When any sound coming from a sound source is incident on our outer ear, it goes through multiple reflections and bouncing off. So from the outer edge of the ear to the inner edge, and then ultimately to the ear canal. So what happens is this outer ear actually acts as a focusing, or we can say a parabolic reflector. It sort of acts as a receiver or a reflector for us humans to collect as much audio energy as possible and focus it inside the ear channel. So all that reflections, like in a room, for example, if I have a sound source, we have reflections from all the walls and bouncing off across the objects. So all that will be can be represented in a form of a filter. Similarly here also. So if I from this sound source to this particular ear, we only have a time delay. If there is anechoic chamber, there is no reflection here, only time delay will be there. My speech source will be almost non-modified, we can say. It will reach here with the direct path, so some time delay and some energy difference. But what happens once it reaches the ear pinna, it will go through multiple reflections and bouncing off by the ear pinna structure, and it will finally before entering the ear canal. Now, so this ear pinna, one thing is that is what we are exactly representing as a filter, or we can, that is why it is called as the head related transfer function. So we are representing the overall reflection and all the properties of ear pinna as the head related transfer function, it in the form of a filter. It also gives us localization cues. Some of the structure like bones and all we are having, they will be resonant to some frequencies. So when we have a speech spectrum here, some of the frequencies will be amplified, some will be attenuated, and these will serve as the localization cues by the brain. So we can say like that, when we hear sound from coming, when even if our eyes are closed, when we listen to a sound coming from any direction, we can immediately guess, the our brain does all the signal processing here, so we can immediately guess the direction, and we are sensitive to direction in that way. So our that type of spectrum modification of the sound will be done by the ear pinna. Now obviously as we are saying, for a child, let us say 5 or 6 years old, the size of ear pinna will be small, and for an adult of 25 years old, that it will be different. So we can say the filtering function or the whole properties, physical properties will be varying, and these physical properties only are represented in the form of filter. So the HRTF will also vary. So that is why we have a numerical method where we take the photo and calculate the contours and ridges, all the structure, and based on that we try to predict what could be the HRTF for this person, like that.
Okay, so the next question is from Sayed Arif Ali. In Samsung handset, one feature is coming Dolby Atmos.
Yes.
Is it some sort of a spatial audio processing feature?
Yes, it is also, yeah, sort of, yeah. But before HRTF, we can say, as we are saying, one thing is, yeah, definitely exact technical detail about Samsung, I'm not aware. But according to me, this sound source, as we are digitally manipulating, this is what I'm trying to say here. So this is, we can say, a DSP based method. But in the earlier slides we have seen, we have these conventional methods where we use surround sound. So according to me, conventionally, Dolby has long back a surround sound system. It has those, But recently, obviously, with the technology now, we are including everything. So it is becoming more of an umbrella term. We have the digital system algorithms also in Dolby Atmos, and I think they are using as of now. They are having both the features. It will come with HRTF and binaural methods also, and it will come with these methods also, depending on the requirement finally. So that should be HRTF based method only. That should be according to me.
So next question is from Miss Rohin Nisa. For she's asking for journal speech enhancement scenario, can we collect speech audio signal with the help of a smartphone to build dataset? So later we can resample the signal accordingly to the specified sampling frequency.
She's asking, can we collect database to? Can we use smartphone to make a database? That's
Yes.
yeah. So one thing is depending on the final goal. So most of the mobile phones will come with single mic, and so single channel speech enhancement based algorithms. If you are targeting, you can use them definitely. Now smartphones are coming with good quality mics and good A to D sampling rates also. They support very good sampling rates. That is one thing. So, but in case if your mobile phone is supporting only, you are saying, okay, we can simplify this question. You are asking if I commercial smartphones nowadays they are coming with very good microphones and sampling rates up to 48 kilohertz also, but I don't think we need to go further in algorithms above 48K. But if you are saying that you record at 16K, later you want to resample it to 48K, so that is not an advisable thing, because even if you resample, the original spectrum is only up to 16K. So depending on your final application, so the if you are having this, for example, this 3D audio or special audio, so we recommend to work at a higher sampling rate only. But if but in case if you have some need to work at 48K, it is not advisable to record at 8K and then resample it at 48K. Better start with the good quality setup which is having 48K sampling rate. But at the same time, current smartphones actually support up to 48K and they have good quality mics, so not a problem. In case you need up to multi-channel speech enhancement like this, we are saying some applications we'll see in the next slides, they actually demand multi-channel speech enhancement. In that case, smartphones obviously cannot support, only single mic we are having, so that could not be a good practice. And second thing is, as you are saying, again depends on DSP and neural network based. In neural network based, some algorithms are there which convert SD to HD, we can say, from low bandwidth to high bandwidth speech signal. But again, that is a complicated. So I will say, depending on your end application, what is the requirement of the sampling rate? Based on that, you can definitely build up the database. Yeah.
So next question is, what is the role of spatial audio in AR, VR application and gaming?
Okay. So here we have seen this case. We'll go back to this diagram here, let us say. So as we are saying that, so let us say this particular point we are considering, from the user it is in center. Here we go towards the left, and toward, from user point of view, this is left side and right side here. So this point, let us say every time we are varying 10 and 20 degrees here. So let us say this user is having a mobile phone or in virtual gaming or virtual reality. So this person is playing a game where it has a helicopter and the helicopter is flying above the head in a spiral motion. So how will we generate the 3D audio here? What we'll do is, from the user's screen, we'll take the XY coordinates or Z coordinates also, depending on the object. And then those XY coordinates, respective to the coordinates or position of the source, we'll fetch the corresponding HRTF, which is already in the database, and then we'll do the convolution. Basically, we take a mono sound source and do the convolution of with these filters. Filters are called HRTF, but this is basically a filter which represents the special property. So we can do the convolution, and when the person is playing the games, definitely when we are using these headphones, that space property, yeah, will be conveyed. So this is one of the applications.
Okay. So the last question on the chat box is, can you suggest some MLDL methods to generate spatial audio?
You are saying machine learning and deep learning based methods. Yes, yeah, methods are there. So here we'll see again, if we look at this slide here. So basically, there are three parts in spatial audio. First part is we are having this simple mono file, and we are doing our space representation is in the form of database here, and here we have the regeneration of audio again. So we can use MLAI at any stage, but this is the most common usage of MLAI here. So as I once said that HRTF database we can record using DSP techniques, simple techniques, and store. Another approach, as I said, for individual, like from a child to adult, we have individual HRTF. There we want to use ML based. What happens is in universities and institutes across the world, we have average databases. Let us say any researcher has taken some requested 50 people to do the recordings. Obviously, this is a very, very tedious process. If if we use a dummy head here or if we use a human here, the person can record maximum up to 100 points or 200 points or something like that in space. So let us say the researchers has requested 50 people to sit and give the recordings. In that case, then they take the average of those filters, all the 50 filters, and for each point they give the filters. So this is again depending on the height and the weight and the race also. Depending on the researcher, it will be different. So what we have available in open literature in universities and institutes is an average representation of HRTF depending on the maximal possibility at that particular time. So here, this particular approach, when we are saying we'll take a picture of the ear of the person using some either numerical method or MLBI AI based approach, using the average HRTF and the person's picture of the ear, we will try to calculate some individual HRTF, and that should improve the user experience. So this is one point. And apart from this, here using at the time of using the speech data here and reproduction, there are also, but there I think the improvement is very minor. So we mainly focus on this part only. Using MLAI at the time of reproduction of audio or recording of audio. That is a standard process, and that will not yield. It is not that much bring that much impact in the final experience as it is advisable to use the HRTF. Yeah, that's it. I think.
So thank you. Now, I think there's no question in this session now. Uh,
Okay.
what we can do if we can take 10 minutes break, so and
Okay.
if you wish, and then we'll continue at it's 7:50, so we can continue at 8 p.m. for the second part of the session.
Yeah.
Yeah,
Sure.
please participants, please be online. You can mute your mic and be online. So we'll continue after
There
10
is a
minutes.
voice break. I think here. We'll join back at 8. No problem.
Yeah, yeah. Okay, okay.
Okay.
Thank you. So participants, please be online. After at 8 we'll start. Okay.
We'll wait for another 2-3 minutes, or can we start?
Yeah. Can we start now if you're ready?
Yeah, we can start in one
Yeah.
second. 1 second. I'll share my screen again.
Yes, yes.
Okay. So for today we have already covered special audio. This is our second topic, source separation. So as in the beginning, I have said we have seen one particular picture, Do we need to stop? No, right?
No, you can continue, please.
Okay, sorry, some disturbance. Okay, so in the beginning of the PPT, we have seen this diagram. So here, what we are saying is that our intended or the desired speech signal is corrupted by or interfered by the background noises. So the in general speech terminology, we call these as interference. So for voice-enabled devices, voice has to be recognized properly either locally or in the cloud. So what happens is when we are using a wake word, so that is why we need to have a speech enhancement in first place. So what happens is we need to suppress the interference or any type of background noise, and this is we can say one of the few areas now, as we discussed in the question answer session. We have single channel based speech enhancement, and we have microphone array. Microphone array is, we say that it is a group of microphones placed in a certain manner. So when we have multiple microphones, that is called as a multi-channel speech enhancement. So this is one of the few areas which is still using multi-channel speech enhancement. Most of the deep learning and machine learning based methods are single channel speech enhancement, where we call that as, we can use, say the name as clear calling or something. But in case of multi-channel speech enhancement, we if we use a beamformer, we need to know the geometry and the placing of the microphone array, and then we use a beamformer to do clean voice processing. So beamforming is one of the types of multi-channel speech enhancement. Another type is source separation. So in source separation, what happens is the knowledge of the number of mics, the geometry of the array, or the relative placement of the microphones is not needed. So we also call it as the blind source separation. Blind means no knowledge about the microphone array is needed, as against the beamformer. So when we are using multi-channel speech enhancement, we still, as I said, single channel speech enhancement is one area where machine learning and deep learning based methods have taken up a lot of dominance. But multi-channel speech enhancement is still an area where there's a lot of scope, and the most of the performance is coming with DSP algorithms. So this is still a DSP dominated area. So when we are saying multi-channel speech enhancement, source separation is one type. So the intention of source separation is we have two speakers here, and we want to separate the sounds. So here our microphones are picking up all the sounds. So we'll see what help does source separation do for voice enabled devices. So one more case, as we mentioned, is, for example, we are saying to Alexa, play the music. So any song or any music is being played. So in addition to the commands which we are giving to the device, there is music. So obviously we are referring these sources as interference or noises. All of these are noises, clutter noise or fan noise or any type of noise. But the music which is being coming through the device, this is called as the echo. Whatever is coming through the loudspeaker and of the device and captured by the microphone array is called the echo. So one more application of that is called as acoustic echo cancellation, but still it will come under speech enhancement only. So even if the music is playing, I want the device to recognize the command and do the needful passing the command to the cloud. So acoustic echo cancellation or interference suppression or noise suppression or anything is still, we can say, dominated area, we can say, by acoustics or DSP based techniques. So one of them is source separation. One of the main techniques in multi-channel speech enhancement is source separation. We'll see how source separation is helping us to do the speech enhancement here. So this is a typical example where blind source separation can be allowed. So there's a term used, cocktail party problem or attention selectivity. Why we use a cocktail in a scenario of a cocktail party, when we have a lot of human speakers in a party, even with all the people in the party, if a person one is talking to a person two will be able to focus or do attention selectivity to focus on the talk of person one. So that is, that ability of attention selectivity is very unique to human beings, and we want our devices or automated devices to have that type of capacity. So the purpose of developing attention selectivity for sound, especially in devices, is a very good or is still a challenging problem. The way humans can focus on the another person with whom they are conversing amidst all the noises in a cocktail party. Same way, we want our device to be able to hear to the intended sound. That type of capability we want to develop using attention selectivity. And blind source separation is one of the mechanism, or we can say old research areas, which still tries these things. So when let us say again, as we are saying here in let us say cocktail party problem, or any in a room we have a TV noise playing, we have microwave noise, or similarly we have vacuum cleaner noise, similar type of. So microphones are here and two people are talking apart from the noises, so that comes almost like not a party but almost like a household common scenario problem, where we have two people, this person is talking some gibberish and this person is giving Alexa the commands. So both the sound signals are going for the microphones, and this microphone will obviously add up these two signals. So output signal, observed signal by mic 1 will be an addition of the two signals, two sources. Similarly for this microphone also, we'll have two sources here and it will be an addition. Now these two signals are having both, this is a simple and obvious, a very obvious explanation. What happens when we keep our DUT devices in a cluttered noise environment? The output will consist of the addition of all the possible sound sources. We can have n number of sources, and microphone 1 will pick up the addition of all the sound sources in the room. So as we are saying, our intention is to make a device such that it has attention selectivity. So we'll see once I have the access only a mixture of signals, we have a mixture of signals. From that, how can we separate our desired signal? So it has application definitely in automatic speech recognition system. It has applications in voice calling. So now we have this feature called clear calling. It is an MLAI based solution. It is coming in most of the mobile phones. So if we are outside in traffic or we are in a marketplace and we are calling, so the way we are trying to blur the background in a video call, similarly we can try to blur the background in audio also. Audio background can be blurred, and that is called a clear calling. So again, there we are having ML and DSP based. So source separation is a DSP based technique, and I have primarily worked on a speech recognition system where our echo dot device will be connected to the cloud. So what happens is, again, as soon as we have any interfering noise, the performance or the recognition rate of this ASR system falls dramatically. Performance become extremely poor, and ultimately to a point that the device is actually of no use. So it is almost impossible to avoid attention selectivity. It is almost we can say indispensable to make the device non-intelligent. We have to impose this type source separation capabilities in the devices, automatic devices. We'll see it how. So again, this is a very simple diagram. We have three users, we have three mics. So for every mic, we have three inputs, and all of them are added similarly here. So this all the mechanism can be represented in terms of filters, as we say. So from source 1 to mic 1, we have a filter H11. Similarly, from source number 2 to mic number 1, source number 3 to, like that. So for all of this path, any type of transmission path from source 1 to sensor 1 or mic 1, here we have a filter representation. This is the intended path, and these are the crosstalk or another path we are having here. Similarly here, the addition. So the first part, this first part by which the sounds are getting automatically mixed, this is called as a mixing system. And once we have the microphones or sensors here, we try to develop a set of demixing filters such that whenever all the microphones are applied demixing filters here, and whenever we'll take input from all the microphones from mic number 1 to 3, let us say here, and all these inputs, mic number 1, 3 and all, after applying, we'll have a final output Y1 to Y3. So ideally Y1 should be equal to the source 1. All the separated source, let us say YP here, should be same as SP. So what we try to do in source separation here is we try to develop a demixing system, a set of demixing filters, which when convolved with the microphone signals, give us the output Y1 to YP, such that the output estimate y1 is as close as possible to the source 1. Similarly, the order could be changed or it could be another order also, but the thing is, ideally the individual output signals should be as close as to the original source signals. So the whole idea of source separation is to develop a set of demixing filters which could give us the separated sources here, which have been added by the environment. So blind source separation enables the extraction of target signal from observed mixture without the knowledge for source positioning and mixing system. Here, it is irrespective of the position and the number of exact number also need not to be known. With that is why it is called as a blind. So what we do here is we have a fundamental assumption of mutual statistical independence. We assume that these sources are independent, and since they are independent, their joint statistics have to be zero. So the fundamental assumption of mutual statistical independence of source signal is there. It implies that the joint moments or the joint statistics of the signals should be zero. So what we do is we try to form from the observed signals, we try to form the joint statistics. We use adaptive filters here. We use arbitrary initial value, and iteratively we try to bring the joint moments of these output signals to be zero in a step-by-step manner. The separation is achieved by forcing the output signals y1 to yn to be mutually statistically decoupled up to the joint moments of a certain order. So we have the moments. If so, basically, source separation is a statistical signal processing approach where we have moments like mean, correlation, cross correlation, and up to we can use higher order statistics also. So what we do is we try to minimize the joint correlation, or we'll say cross correlation. So we'll try to minimize the cross correlation between y1 and yp here. So output signals are forced to be mutually statistically independent, and the joint moments are decoupled up to a certain order. So this is the basic fundamental principle. We have to remember only two things: sources are independent and their joint statistics have to be zero. Now, there is one more challenge for in a, when we talk about speech. Speech will be almost always accompanied by reverberation. Most of the time, DUT devices will be used in home. Echo Dot or OK Google, when we are talking, it is in phone also, but most of the devices will be used at home. So this is a simple, very simple example of a reverberation scenario. We have mic number 1 and 2. This is a picture of a room. We have a source here. So this is a direct path. Apart from the direct path, we have a reflection here. We have another reflection here. So apart from the mixture, mic 1 is obviously getting some sound from this source, but its reflections are also there. So here I have a mixture of 3 sources, and also for each source I have the reflections. So for this one source, we have almost around 4 reflections here for mic 1. Similarly for mic 2. In addition to the mixture of my intended signal is the direct path, my signal of interest or the signal of intent, desired signal is the signal from the direct path to the mic number 1. And but we have competing sources here. We have mixture of speech sources, and all these speech sources will have some, let us say on an average 2 to 3 reflections. So now mic 1 and 2 are having interference as well as reverberation. So that is one challenge. This type of mixture, which we call, is referred as convolutive mixtures, where we are having reverberation in scenario. So we have reverberation in addition to interference in an indoor environment. Multiple reflections of original signal means assumption of the independence is not valid. My direct path signal here and its reflection, these two are not independent. So the assumption of independence is not valid. So that is why ASR systems are very sensitive to reverberation. So our problem definition is like we want to do speech enhancement for ASR systems using 2-mic convolutive BSS. So what we have contributed is a convolutive BSS which takes care of interference as well as reverberation. So we have used second order statistics. We have tried to decorrelate the signal, minimizing cross correlation over multiple time lags. We have used a steepest descent algorithm here. So this is the mathematical formulation, how we are doing. So there's a mixing system, as we have seen, demixing. Mixing system can be represented in form of this equation. We need not to understand the exact detail here. Again, demixing system is also a set of filters. Each filter is convolved with the sensor signal. and this is the cost function. So this is an information theoretic where the y, we have the output signal as y. So output signals are represented in terms of matrix y, and the cross correlation of these y hat into y. So this is a cross correlation matrix. We try to minimize the relation between them. Uh, the, this is the set of demixing filters which we are trying to estimate. So here we start with an initial value of 100, and then we use an adaptive filter, is a steepest descent approach to estimate the filter. So it's an iterative algorithm which eliminates cross correlation between the output signals here. So we can understand and focus only on this part. We need to develop demixing system using adaptive filter theory and minimizing cross correlation. So again, this is a simple example here, as I said. So here we have a mixture signal, and after applying the algorithm, we have output one, source separation output one, and source separation output two. I'll be trying to play it again. If there's any issue, please let me know.
That stinging vapor was caused by chloride vapor.
Mixture signal is having two signals, male speech and female speech. I'll play it again.
That stinging vapor was caused by chloride vapor.
Now I'll play output one after passing through the algorithm.
We could barely see the fjords through the snow flurries. That stinging vapor was caused by chloride vapor.
Is the impact clear here?
That stinging vapor was caused by chloride vapor.
I need some input actually. I'm not able to listen to any voice. Am I audible? I think there's some problem.
Audible, ma'am. Audible.
Audible, madam.
Okay, so the output signals are clear. Should I play them again?
Output was clear.
Okay, we can move to the next slide then. Okay. Again, I'll mail these files also. So again, as I said, this is a mixture of signals, and these are the separated signals. I can play once again. Okay.
We could barely see the fjords through the snow flurries.
This is again output number 2.
That stinging vapor was caused by chloride vapor.
We'll listen to the mixture signal once again. This was the original
That
noise.
stinging vapor was caused by chloride vapor.
Okay. Okay, so we'll move back to the next source here. So this was all about source separation. Source separation is one of the very, very challenging problems still. Here we are using only 2 sources. We can have up to 8 or 9 sources in a room, and separating each of them, it will be an intensive task, but we do have that capacity also. So we'll come to the third topic of today. This is time delay estimation. So as we have seen, all of these are multi-channel algorithms. Time delay estimation is also a multi-channel algorithm. We'll have a brief background. I'll try to explain somewhat why we need time delay estimation, what is the context. So time delay estimation is an imperative or a fundamental requirement for passive acoustic localization. I think we all must be familiar. Just to cover everybody's, we can say, perspective, I will try to define it, just taking 1 or 2 minutes. What is passive acoustic localization? So if we come to this diagram, we see that the sound source is having some position specific to the microphone array, r, theta, and phi. So if we use the microphone array signals to determine the position of sound source and estimate any of the parameters, r, theta, and phi, that is called localization. Localization is the process of determining the distance and direction of a target using acoustic waves and transducer. That is why we call it as acoustic. So we have active localization, where we transmit a signal from, obviously with mics we cannot transmit. If we have some other transducers, we transmit a signal and wait for the reflection. Then we call it as active localization. That is called echo ranging. And when we are only listening to the sound produced by the source and we try to localize, it is called passive localization. So, time delay estimation is important for active localization as well as passive, both. It is imperative and it is one of the key principles, key concepts on which localization is based. As we have seen in 3D audio impact also, the location information of any source is encoded in the time delay across the microphone array. So active localization and passive localization both use time delay estimation. When we are using only, we are listening to the sound sources, that time we call as listening or passive localization. We'll be covering time delay estimation for passive localization, passive acoustic localization. So why do we need acoustic localization? That is one thing. We all are familiar with GPS and other systems also, localization systems. So what is the need of acoustic localization? So this is first example. This is an example of a bat transmitting a sound. This is active localization, transmitting a sound and waiting for the reflection to estimate the position of the prey. Similarly, in underwater acoustics, we have a dolphin, and then again it is trying to localize the prey using the sound and the reflection. This is an example of a submarine. Using these two concepts, we have submarine here. A submarine will use and the active localization again here to try to estimate and navigate. Basically, for navigation and traveling, it will use the sound waves. So the need for acoustic localization is some applications as speech, they are inherently acoustic in nature. So if I have to localize a speaker in a room, for example, I have a auto directive camera, which we have 10 speakers in a video conferencing application. I have an auto directive camera which rotates to the active speaker. So first what we'll do with the microphone array, we'll localize the active speaker and the camera can turn towards the person. So some applications like speech, breaking of glass, intruder detection, some are definitely inherently acoustic. Second thing is for underwater applications, deep sea drilling, and there light waves or EM waves, basically electromagnetic waves, cannot travel after certain depth. We have to rely on sound waves. So that is why we need acoustic localization, as we have seen here in submarine example. Another case is we have deep sea oil exploration activities where we have oil tanks and all. Inside a oil tank, we need to do inspection and maintenance. For that, we use robotic platforms. And in an oil medium or a petrol medium, it is not advisable to use EM waves because of the inflammable nature of the environment here. So sound waves are preferred there. So whenever we have a liquid medium, it's generally, and this is an example or a picture of an avalanche here in Himalayan regions, snow avalanche in Himalayan regions. So these avalanche will generally emit infrasound and acoustic waves. So we have this avalanche, it is an example of an avalanche monitoring system. In mountains, we have these infrasonic sensors which can actually sense if there's an infrasonic wave, so that timely estimate of the location can be made and timely warning to the nearby population can be made. So snow avalanche monitoring system are also acoustic based. So basically it is applications. Some applications need acoustic localization and it is important. So passive acoustic localization is one of the key methods which is used for predicting or the location or for snow avalanches and traveling also. The speed and everything can be predicted. This is an example again of a ship which is far away from the territory, and it again it has some another object. So mapping speed and velocity or trajectory mapping can be done using this principle. So generally ships will rely also ship to ship communication or submarine identifying the location of another objects nearby. That is done using acoustic techniques. So acoustic localization is important. It's generally not as common as GPS, but obviously it is needed, and that is why we are talking about time delay estimation. And as compared to EM waves, when we talk about EM waves, they travel at a very high speed and time delay is negligible. As compared to sound waves, we have a significant magnitude of time delay estimation that can be used. These techniques are specific to acoustic or sound waves. These are not in general for EM waves, because EM waves time difference is not at all observable for us. So these are the applications of acoustic localization. So as I have mentioned, surveillance, breaking of glass, intruder detection, residential security. This is one of the most prominent applications of acoustic localization. In underwater acoustics, we have target localization, deep sea drilling, oil tank inspection. In robotics, a robot has to navigate to a master. Now we have commercial toy robots which play with the child, and basically it has to navigate towards the master. So the artificial ears will be working using acoustic principle. Similarly, automatic unmanned vehicles and remote vehicles. In smart home systems, we have applications in video conferencing and speaker localization. In seismology, we have another when we try to study the structure of the earth crust, internal structure of earth crust, we transmit sound waves and wait for the reflection. So it helps us to study the structure. There's a good application in seismology. Localization of seismic events is there. In control systems also. Similarly, in biomedical engineering, we all are familiar with ultrasound and other applications. Detection of abnormalities. Similarly, for study of brain waves and EEGs also. Any type of study related to the material structure or metal structure inside human body is involved. Sound waves are involved there, and localization principles are also used there. So time delay estimation will come back. These are three examples of transducers. This we are familiar, everybody is familiar with this microphone. There, when we have a microphone for water, we call it as hydrophone. This is one of the example which is used in commercial water tanks. Similarly, we have a geophone for study of seismic activities. This is one of the example, very old picture. It is here used as a geophone in seismology. Okay, so we'll come back to acoustic localization techniques as we have seen this diagram earlier. Similar, if I have a sound source here. Now, since we are talking about passive localization, we are simply receiving the sound waves from the sound source. So we have three microphones here, and we have seen that these waves or sound waves received at the microphones carry information about the property or special location of sound source in the amplitude and time delay. So for first microphone, my signal received will be latest and shortest in amplitude. Mic number 2 will have somewhere in between, and mic number 3 will be first signal to arrive and would be the largest. So we have some amplitude info. So this is a very conceptual level diagram. It's a very simplified and elementary diagram for time delay estimation, localization principle. So here we have some amplitude information as well as the time delay information here at the receive microphones. Now, if I am representing mic number 1, 2, 3 as the circle and I'm trying to draw, what happens is for mic number 2 and 3, I have a time delay here, 2, 3. We can represent it as T and mic number 2 and 3. This is a simple equation. We can leave that. For mic number 2 and 3, the locus of point which gives us a constant time delay. I have observed the signals in mic in 2 and 3 and I have calculated the difference from the graph. For mic number 2 and 3, the locus of points which give us a constant time delay is this hyperbola 2, 3. Similarly, for mic number 1 and 2, the locus of points which gives me a constant time difference is another hyperbola. So the intersection of these two hyperbolas is having my location information. This is the location of the source. So this is the simple equation of time delay, and this is the equation of hyperbola. Similarly, this is of another hyperbola. Intersection of, so we can employ multiple sensors here and then use the intersection points. So similarly now will come. So if here we have ignored in this equation we have ignored the energy, focus on time delay 2, 3 and 1, 2 here. Now, if we ignore the time delay part and focus on the energy difference or amplitude difference will ultimately lead to energy difference here. So similarly here for mic number 2 and 3, this diagram might not be mathematically correct, only for explanation I'm using. So for mic number 2 and 3, the locus of points which give me an energy difference. So I have here R2, 1 by R1, 1 by R2, 1 by R2 and 1 by R3. It will become R2 square and R3 square for energy. Locus of points which give me the constant energy ratio is this circle. Locus of points again for mic number 1 and 2. For constant energy ratio is second circle, and the intersection we can use as for the location of the source. Now, if from the first diagram we have the time based location, we have the energy. Now, if I combine for mic number one and two, I combine time delay based locus and the energy based locus. I have one location. We need not to have the mic number three here. So this is the principle which humans use. For a human head, we have left ear and right ear. We use the localization cues called time difference, energy difference, and this is somewhat similar concept. We try to localize the sound source here using two. So with the if we have more and more information, we can reduce the number of sensors and use this. Now, how we are calculating the time difference? So, suppose I have more sensors here. I have a linear array, mic number 1 to m here. We have a source at any point in space, r and theta. So, the travel time measurement of acoustic signal across multiple sensors is weighted by the speed of sound to obtain an equivalent range difference. If I somehow measure the time difference and multiplied by the speed of sound, I'll obtain an equivalent range difference and then calculate the point where the source is located. How to measure the measure the time difference? So time difference of arrival can be measured using, again, these techniques are for passive acoustic localization. Time difference of arrival can be measured using these techniques. One of the most famous and one of the most commonly used technique is beamforming. Then we have generalized cross correlation approach. We have Hilbert transform based cross correlation. We have eigenvalue based decomposition, and then we have Capstral pre-filtering. So what we are trying to do here is basically beamforming. If is again it's an advanced concept. What we try to do is, if I have a M sensor array for this, so for sensor number 1 and 2, I have time delay 1 2. For 2 3, I have 2 3. Similarly, I have 3 4 up to all the travel time I am having here. And this can be combined in the form of a vector. We can have a time delay vector. So what we have to do is, what a beamformer does is, if I have a M sensor microphone array, a beamformer will basically search in all the directions, which direction is giving me the maximum received power or energy. That I will associate that direction with the time delay. What I'll do is, I will try by hit and trial. We try to shift the time delay for all the microphones, and when we reach to a point where we have the maximum reception of energy, we say that this is the direction which we are looking. So to be able to estimate time delay, for example, if I have only one pair, microphone 1 and 2, we have only one dimensional estimation. If I have microphone 1 2 3, I have two quantities and I'll have two dimensional. So for M sensor array, I have a m minus 1 dimensional estimation. My vector here is an m minus 1 dimensional time delay vector. For this, I need to estimate and employ a m minus 1 dimensional peak detector. So what we have to do is, we have to search for maximum energy in m minus 1 dimensional peak detector. The beamformer will search for all the possible values of time delay in this m minus 1 dimensional time delay vector, where it can get the maximum received power for the source position. That particular vector we'll say is my time delay vector. Now searching for real-time applications. This is one of the application. Beamformer is definitely when we have, if we can do offline processing, or for example, if we have very strict requirements for accuracy, we can definitely search in an m-1 directional peak detector. But sometimes it is not possible. Real-time applications in audio, in voice calling, we need minimum delay, minimum lag for the voice to be processed. In that case, we have to estimate each of the time delays individually. So rather than estimating this as a vector, we can estimate them individually. So, okay, beamformer is our m-1 dimensional peak detector. Generalized cross correlation, if I take the signal from mic number 1 and 2 and do the cross correlation. So we have several one-dimensional peak detectors. Mathematically, this beamformer approach is always more efficient and computationally expensive. And cross correlation based approach is computationally very simple but less efficient. So we need to have mathematical or statistical signal processing based approach. For real-time applications, what we do is, we take several one-dimensional peak detectors which are computationally simple and combine them to achieve efficiency as equal to the m minus 1 dimensional peak detector. So one of the techniques in statistical signal processing, that is called as the Gauss-Markov estimate. What Gauss-Markov estimate does is it takes a generalized cross-correlator approach and then combine those time delays using the error matrix. So if, for example, this is a simple equation of a cross-correlator, we take two signals, microphone 1 and 2, S1 and S2. We do the cross correlation. So my cross correlation based time delay estimate will be original time delay estimate plus some error here. So what we do here is this error matrix or the covariance matrix of my cross correlation. We use the statistics of the cross correlator here, this error matrix, and try to, using this, we try to combine this again and get in. So our objective is to estimate optimal m minus 1 component time delay vector from the cross correlation based time delay estimates. This is the equation for a Gauss. We need not to go into the detail again here. We want to estimate the optimal time delay from cross. We have this cross correlation vector here. We are using the error matrix or covariance matrix here to estimate the optimal time delay. We just need to remember three concepts here. We have the error matrix or statistics. We have the statistics of the cross correlator. We have the time delay from cross correlator, and we combine these two to get an optimal estimate for the beam forward. So this is one of the cases where we have done simulations and tried to see. So we have proposed a Gauss-Markov estimate based optimal time delay vector estimation method. Simply we have a source here. We have three sensor arrays, sensor 1, 2, 3, and this is having some time delay here, some distances here. So we have a wide Gaussian noise source signal, and sensor signal is also wide Gaussian noise. These are the bandwidths. Range and bearing are there. We vary the SNR, and we use for localize. So once we have estimated the time delay for this three sensor array, mic number 1, 2, 3. We have these time delays 1, 2, and 2, 3. So if I have the time delay, we have a method called wavefront curvature method for near field. If my source is in near field, we have a linear array of three sensors. So this wavefront curvature method gives us the formula of range and theta. So using this time delay, we calculate the range R, the middle sensor distance R, range we are calculating, and similarly we calculate the theta. So what we do is we estimate R and theta using the cross correlator based approaches and similar time delays, and then Gauss-Markov estimate based approaches also, and then we compare these two results of R and theta. So these are some of the results, proposed Gauss-Markov versus an older version of Gauss-Markov here. So we have time delay estimate comparison here. We have the range of SNR and mean square error improvement. So for different ranges, these are, if this is the theta, what is the percentage improvement in range, time delay, and range and bearing I will be getting. This is the experimental setup. We are having, this is a lab-based setup here. We have three microphones here. We have two loudspeakers here. So these two loudspeakers are used for conducting the experiments. These three microphones are here. We can go in detail as and when required. I'm trying to cover it in more of a simplified overview here. So for this particular loudspeaker, we are trying to localize in experiments. And these are the equipments which we have used. This is the Sennheiser mic. Some speakers are there. This is a data acquisition system from National Instruments. These are the preamplifiers. So in this experiment, what we have done is, we have compared the percentage mean square improvement in the percentage accuracy. For basically, we want percentage accuracy improvement in the estimate of range and bearing. So for different SNRs, for different ranges, for this particular SNR, let us say 8 dB, we vary the range, and for each range we see the mean square error improvement. Similarly, we see here. So at high SNRs, there is hardly any improvement when we are using cross correlator based time delay estimates, or we are using Gauss-Markov estimate based time delay. So higher SNRs, these are same. At lower SNRs, at let us say from 12 dB onwards, our original range, let us say here we are having a 4% improvement in the mean square error from the original estimate versus the Gauss-Markov estimate. So again, for different ranges, as our source, so range is one, as our source moves away from 1.5 to 4 meters, SNR power will decrease definitely. Improvement will be more. If we have at low SNR further here 0 dB, then again our improvement will be more. At higher SNR it will be same. Similarly, so here for a particular SNR, as the source moves away further, range increases, improvement is more. Similarly here for a particular range, let us say this range is 4 meter we take, not 4, it's not 1.5 meter. For particular range, as we decrease the SNR, the improvement is more. So whenever we have a low SNR, either due to when our source is moving away or the power is decreasing, we have more improvement. It means similarly bearing. So here the improvement in range R and here theta. So range R, let us say 12% improvement is here. This is less. So range is more sensitive to SNR as or improvement as compared to bearing for time delay. In when we have a certain same time for this is the time delay estimate. 1, 2, and 2, 3 we have taken the average. So this is the mean square percentage error improvement in time delay for increasing range here. If we are going from this blue color to yellow color, range is increasing, and here SNR is decreasing. So for a certain time delay, let us say I'm getting here 6 to 7% of improvement here. So for the same time delay improvement, my bearing or angle improvement is less and range improvement is more. So we can say that range is more sensitive to time delay errors as compared to bearing. Whenever the SNR decreases or the range decreases, time delay error will increase. Similarly, for whatever reasons, background noise is increasing. So when the SNR decreases or the background noise increases, we'll have certain errors in time delay, and those time delay errors will lead to errors in the angle estimate, bearing estimate, and range will be more sensitive to than bearing to the time delay errors. Another thing here is so we have conducted this experiment for various SNRs, various ranges, and two positions of angle also. These are the estimates of PSD. So we have seen that we estimate some time delay and we use the statistics of the time delay error, cross correlator statistics. So that statistics is PSD. Basically, we are trying to estimate the PSD here. So this is an estimate of PSD given for various same set of parameters in the experiment. This is the after simulations. This is the experiment which was conducted to validate the same results, whether they are not. So this is a schematic diagram of this particular whole setup. We have this national instrument system here. We have the loudspeakers here. We have the microphones here. So this is the plan, or we can say the map of this particular diagram. After the initial establishment of all the placements of mic, we are using this particular speaker, second speaker circle, to conduct the time delay experiment. These two speakers are used where because to establish to localize mic in field, it is difficult. It is very, very difficult to correctly place the microphones. So we have a method called, I think there's some standard, I am actually forgetting the name. There's a method where we use two loudspeakers to transmit the sounds and first establish the positions, finding the positions of the sensors here. Once we have these coordinates, after that we use this speaker, second loudspeaker, to conduct the rest of the experiment and establish the utility of the Gauss-Markov estimate. So basically, this is a theoretical work where we have established both the simulations and the experimental work. So these are some of the equipments which we have been using here. These are simple Sennheiser mics used in the experiments. This is a national instrument system that can support up to very high sampling rate. We have pre-amplifiers. We have the required cables. Yeah, so I think that's it for this. Yes, that's it for this. We can take up questions.
Okay, so now there's a question from Dr. Sunil. He's asking, speaker diarization can multi-channel perspective mode or not? I cannot pronounce this. What is
speaker diarization? Yeah, actually, I have never worked on this field. I'm not sure whether, in general, from papers, it is always possible. And if we can say something about application, we can. I myself have not worked on this particular problem.
okay? So the other question is, what will be the effect when mic near the source has more noise intensity and compared to other source? what will be the effect when mic near the source has more noise intensity compared to other source?
Yeah, in general, okay, when we are saying that the noise field is not uniform and it is different, yes, it is not, it's a non uniform noise field. So if we come again, if we consider the conventional DSP based methods, they all assume microphone array based methods, beamforming methods, they generally assume that the noise field is isotropic. It is same at all the sensors in general. And only for this particular time delay estimate cost Markov, we conducted an experiment where, for example, in a typical scenario, we have a mic array in a sonar or in underwater scenario. We have deployed a mic array, and after that, one microphone has undergone malfunctioning. It has higher sensor noise, internal noise, as compared to others. That time, we have seen the impact on cross correlation and Gauss Markov estimate or time delay estimate. That obviously, according to as the noise increases, the variance of the time delay estimate and localization will increase. The accuracy will decrease definitely, but there has to be, again, depending on our statistical signal processing algorithm, we need to have some information, like for example in our Gauss Markov estimate, we are taking care that we are using the noise PSD. So if I measure, for example, here if we say mic number 3 has a higher sensor noise and these two are having low noise. So we are using the PSD here, internal PSD. So as long as we are using the statistics of the observed signal and our model is taking care of that, it should not be impacted. The algorithm should be working fine. But in case, for example, we are working on neural network based approaches, multi-channel, our modeling itself is not taking care of that, then I think it will be a problem. The general beamforming solutions, delay sum, super directive, they do not assume. They by default, we do not take care of this type of abnormality there. So then in that case, the performance will decrease.
Okay, so next one is we have angle of arrival and TDOA, time difference of arrival.
Yes.
So under which situation we should use AOA, TDOA for real time application?
Angle of arrival can be used only when we have a source in far field. So when we have a far field source, that means if we look at this diagram here, so we have a linear mic array here, sensor 1, 2, 3. We have a source here. So when my source to sensor distance, this range R, is very much larger than the dimension of the array L. R is much greater than L. Then we can assume that the source is in the far field. So that means R1, R2, and R3 are almost equal. Far field only angle. So all the ranges will be almost equal. In that case, we can use angle of arrival. If our source is in near field, the distance R is comparable to L. It is not much greater than L. In that case, we can actually estimate range here. Range R can be estimated. And for example, here, if I am from source to these microphone array, we have a wavefront curvature here, spherical field. So when we have a wavefront curvature here, then only we can estimate the range R using the wavefront curvature method. We can estimate theta in any case. But if my source is in far field here, these all will be planar wavefronts. There will be no curvature here. We cannot estimate R. So if we want to estimate range R, then we need to have definitely time delay of arrival. For range estimation is possible only in near field. And for range estimation, we definitely need time delay of arrival. For range and angle, both can be estimated simultaneously. For a far field source, only angle can be estimated, and then we call it as the angle of arrival estimation for far field.
Okay. Okay, thank you. Next question is from Mr. Yash. He's asking, can you please elaborate on dimensionality of sound? Can we differentiate between two sounds of different dimensions, like hearing 3D and 4D sounds? There are two parts actually.
Okay.
Here, Sunil want to ask in a audio mode. So maybe we can take that question first.
Okay, okay, no problem.
Dr. Sunil, please ask. You have raised hand.
Yeah. Uh, Very nice talk, madam. You have mentioned very nicely, and we are doing. I have already done my research work on digital signal processing using Marathi language.
Okay, okay, okay.
Okay, but one of my students is working on a speaker diarization of two languages, as well Marathi as well as Hindi.
Okay.
And can we use the localization for the same in that research?
Actually, I have never worked on speaker diarization myself. So, just to give a quick context, I think in the beginning we talked that we have two parts, as we are saying, acoustics and speech. So, I have more experience in acoustics and front end signal processing. So, again, as diarization, I am very not sure means what algorithm will lead to what type of results. So I think I am not experienced enough to help on this. I'm not sure what changes you will experience like that. That is not my expertise actually.
Okay, thank you. So now we can take the question in the
Okay.
chat box. That is,
Thank you.
can you please elaborate on dimensionality of sound? Means, can you differentiate between two sounds of different dimensions like hearing 3D and 4D sounds?
I would like to understand that what they are implying when they are trying to use the term 3D and 4D. So
Maybe,
uh,
yes, are you there? Can you hear us? Yes? Maybe their mic may not be working.
no problem. I think what we understand from this, we can take understand it this way. Uh, so, take again in literature, some terms are overlapping. There is no clarity about the number of dimensions. So when we are saying 3D audio, so 3D audio means using the audio, I can give the perception of X, Y, and Z, all the three. That is how the name is three dimensional sound. So in three dimensions, X, Y, and Z, any angle. So from left to right, 0 to 180 degree, from this top to bottom, any place the speaker is situated, and I am can perceive that place. 3D sound. That is the concept is. But 3D doesn't mean only like we have 7.1. We can say before the use of binaural or 3D audio or spatial audio, when we had movie theaters, which actually were giving us spatial audio. In movie halls, we do not use headphones. We have the placement of speakers. At home, we have max 7.1 or 5.1. In movie halls, some multiplexes, we had very good placement of speakers, and they can call it 8D or 10D or 16D, whatever. But that is not actually, if in terms of, we can say technically correct term, 3D means XYZ, all the three dimensions we have already covered, right? So that is more of a marketing term when we are saying 8D cinema hall. So uh, we say 10 dimensional cinema hall also in Hyderabad, some theaters claim. This was before, but if we look into the research scholar community, 3D audio means all the 360 degrees in horizontal plane and vertical plane, both we can be experienced. And if the resolution is like say in horizontal plane, we are having 0, 5 degree, 10 degrees, everything is already there. I don't think we need to use the term 4D audio. That is the main source of confusion here. So definitely, but another thing is uh, now we have stereo sound is definitely we are familiar. Mono sound we are familiar. We are familiar with 3D audio. So definitely, user can distinguish between these sounds. Perception is there. I have played the files if there's a problem, and in internet also. If we see we have enough examples, I'll mail this file to Mr. Vajid, and you can take from them. Using headphones, we can definitely perceive. So the whole idea is when I'm sitting in the room, and I have a scene here, and for any entertainment or video gaming, the type of ambience or sounds are coming from different directions. We recreate that type of environment to a listener. That is the concept of 3D audio. It covers all the ambience of the room. I don't think there is a need to for. I could be wrong also, but I don't think there is a need to use the terms which we were using earlier, like 8D audio or 7D audio used by cinema halls. That is more of an advertisement thing.
Okay, so next one is from Dr. Nasir. The question is, please suggest few more problems for scholars. I think he asking research scholars who can work in this area. What are the challenges which should be
Yes. So I will say definitely one thing is recent trend, not recent for past 5 6 years. The trend mostly has been in the domain of machine learning and artificial intelligence, and that has immense capacities. The primary challenges when we talk of machine learning based methods are work very well with single channel speech enhancement in our smartphones. We have single channel speech enhancements. What happens is we are doing voice calling, for example this call only. We are using any office meeting, or we are calling anybody on phone, voice calling. So whatever background sound is there, if we are in traffic, that should be suppressed. So single channel speech enhancement using MLAI is one of the promising areas which now has a lot of demand. And as I said, multi-channel based methods are still slightly DSP. The main reason is for MLAI based methods, we need huge databases, and single channel is still because we can everybody can record using a smartphone and upload. It is easily available. But for multi-channel, it is everybody does not have, the normal users do not have the multi-channel recording setup at home. Microphone array people are not having, and getting that database online from internet is not that easy. You need to create a database. For that, if we create the database, that itself augmenting and segmenting everything will take almost 6 months to 1 year. But our PG students hardly have 1 year for project. Open databases in universities and internet, multi-channel databases are not easily available. So that is a challenge with multi-channel problems. It is slightly difficult. It might be available commercially by paying some amount, but single channel speech enhancements are easy to access, are easily accessible. That is one thing. Second thing is, if since we are going for single channel, MLAI based methods are more suitable, I can say. So there, as I said, speech enhancement definitely is one thing. So context aware noise cancellation, for example, depending on the user requirement, we can have several types of noise. Traffic noise is one of them. Household noise for work from home, if it is there. So suppose in my home I have kept a mic and recorded the usual type of noises, and for those particular noises only I can develop a neural network and cancel the sound. Then it is sufficient. I need not to train my neural network for traffic or construction noise or some other noise, right? That is enough. So context aware, working only for specific cases, small problems we can start. Source separation also, single channel source separation, can, is it possible? Are those there? Some that neural network based approaches also we can use. Direction finding, as we are saying, far field is there. Direction of arrival problems based on machine learning and neural networks, that is also a very interesting and new area. I do not have expertise, but definitely I will also want to work in that area. Do we?
so
Yes.
next one is why only stereo sound we talk? Only two dimensions means only two channel basically. I think any reason behind that?
I think there is some communication gap here. Is the thing is stereo normally conventionally we use headphones or earphones for two sounds, left and right stereo. Now using special audio or 3D audio, we are trying to give all the special information through those two, because obviously we have only 2 ears, right? So with 2 ears only, headphones only, we want to give the impact of 7.1. We want to basically convey the whole. If we see any movie, let us say Triple R or Bahubali movie, animation based, where there is a lot of special information there, and since in movie it is possible also to they take 1 year to make the movie. It is possible also to have a lot of information sounds coming from different direction. Now conventionally, as we are saying, 7.1 system. For some reason, we do not want to use the public system. We need not to purchase the 7.1 system. We can use earphones. Obviously, we have 2 years only, and we want to convey the experience of 7.1 using two earphones. So that is what 3D audio is doing. That is one thing. And second thing is, like, again, in gaming and other applications, there are only at the end while regenerating the sound, there are two options. Either we use a set of loudspeakers around us, or we use headphones. So earphones is a more comfortable or convenient, each for 1 year. So that is why we are having the stereo system here.
Okay, so the next one is, I think same thing is there, related to that only. Are 2 years sufficient for localization? I think human years sufficient for localization.
I think this is understood. We all can localize, no? We humans can definitely localize with 2 years, no?
Okay, and same question like that also. For localization, does the human brain use human intelligence as well, in addition to to sensors? We have two sensors.
We can say like that. In a way, we can say like this. Okay, we'll combine the previous in this question. One thing is, can 2 human years are sufficient? So for humans, definitely 2 years are we can localize a sound as long as it is broadband, any wideband signal, using 2 years. And that is a research area. If humans can localize using 2 years, why devices need microphone array? Why two microphones are not sufficient? Humans can definitely localize. We all know any sound. We have only 2 years, and any sound we can localize using 2 years, right? That is true. Now the thing is, limitation is that source has to be broadband or wideband. If we generate a sine wave or a tonal, then it is not possible for us. For broadband sounds only we can localize. Now, intelligence is again a far concept. More than that, what happens is, as soon as we hear a sound, we turn our head in that direction, right? So for example, if I have localized in the horizontal plane, 0 degree or 90 degree, we'll turn the head, we'll move our eyes. As soon as our eyes locate the source, we fuse these two information. So this is called audio visual impact. So this is also latest in virtual reality, that we have a camera and we have a mic, and we used that information from mics and all. From images or from video, we can use that information from localization. That is also another thing. So that is called, I think, multimodal information based localization. So what we do is, definitely for us humans, for alertness, as soon as we hear a sound, we'll turn our head in that direction. And once our eyes see, okay, this is my line, along the line, elevation or anything, once we suppose this plane for 90 degree, this whole plane is 90 degree. So the elevation we'll find using the eyes. That we do multimodal fusion or information. But even if for people who cannot see, or if it is dark, experiments have proven that as long as the sound source is broadband, with 2 years we can localize. There are other factors also. What happens is, in general, for any living organism, 2 years, other organisms are also there. What they will do is, as soon as they hear a sound, they will try to move the head. So what happens is, when we move the head, ears, for let us say for one placement of the ears, we got some time delay. Then when we move the head, we'll basically trying to create a virtual array. So using the same 2 years, 2-3 samples of time delay we are getting. The source is same at the same place, and we are trying to move the head and getting from different orientations of the ears, we are getting the time delay. So in a way, we create a virtual array, and we can quickly, so that we can quickly get 2-3 samples of, and then we can localize. So that way the intelligence is used. That is how from childhood a child will learn. As eventually it grows, it will learn that type of brain will learn and adapt those type of techniques. But ultimately, if you look from microphone point of view, it is 2 years only. Rest, movement and use of eyes and everything, that is, yeah, use of brain intelligence only. Yeah.
Okay, so I think the other one is, can we use teeth also for hearing and localization as dolphins does? I think dolphin uses the teeth to sense the
Yeah.
vibrations.
I think I have not come across this type of information anywhere till now, but as some of the papers related to not sorry, visually impaired persons, they mention that visually impaired persons sometimes in whenever there's a difficult situation for them, they try to use clicks or tongue clicks and try to find map the environment around them.
Oh, okay, so the other one is, can we assume Pinna as a spatial filter that will filter signals from the backside?
Yes, we can say that. The HRTF, yeah, yes, definitely, we can say that. In
I
fact, ear
yeah,
pinna is a special filter only. It has a filter response for all the directions. The response will be different for sounds coming from front direction and definitely different for sounds coming from the rear direction. Yeah.
yeah, we can take this last question. I think this is also the same. He's asking related to Pinna also, asking how to resolve the front back ambiguity.
Using ear pinna. So for humans, actually that ambiguity is not there, as I just mentioned. As long as the source is wideband and a broadband signal, ambiguity is not there. And ear pinna itself, the transfer function or the filter function for the ear pinna takes care of that. So that is not a problem. But in normal microphone arrays, that problem is still there, and there are methods which various researchers have been trying to work to resolve that. I have not come across any successful method till now. I've tried to implement few papers, but we have not achieved any, we can say, definite success. I will say.
Okay, this one more thing. What skills should I master to work in this field based on your experience? What skill set they required for this?
As of now, yeah, the current, if we are saying field, definitely machine learning and AI based knowledge is definite. Experience in deep learning is required for everybody. Even people who have been working in DSP for 10, 15 years, now we have to work with deep learning methods. So, knowledge, good knowledge of machine learning, deep neural networks, that is must. That is one thing. Second, we need to have little bit of background of DSP, obviously, and some background in acoustics is also needed, depending on the interest, which part you want to work. If you want to work in speech recognition, speaker verification, like those problems, then it might not be required that much. There we use more of, again, data science based techniques. But if you want to work in, let us say, beamforming and all, then acoustics is needed. One another approach, which we are saying, like experimental work, I will say some experimental experience should also be there.
Okay, okay. The other question asking what are the good opportunities in this? Are there good opportunities in the same?
Yeah, we'll say if we go into the speech domain, my domain is acoustics. I'll say speech domain, the opportunities, especially in machine learning, AI based speech domain opportunities are very good. Immense opportunities are there.
Yeah.
Recognition, verification, because all the mobile phones, all the commercial laptops and all, now they are coming with speech based features.
Okay, so Umar sir is yeah.
Yeah.
Sir.
Okay. Thank you, ma'am, for a nice presentation. And I can see that many uh, participants were interested in and they have asked a lot of questions, and you have actually satisfied them with your responses. So this shows that a lot of interest have been evoked in the participants, and I'm sure that if there are any other queries, they can always contact us and we can transfer it to you, and you will be helpful in responding to those specific queries.
Sure,
Uh,
definitely, definitely.
the problem with this presentation and the FDP program that we are having is we are not able to meet face to face, and therefore everything is going on virtual. So if we would have met, then it would have been better, and we would have presented a actual memento for you, and we would have been benefited in interacting over a cup of tea and have more information from you from the experience that you have gathered from the research as well as in the industry. But anyway, to just as a token of appreciation, this is a virtual memento that I would like to present to you, thanking you for the time and effort that you have taken to deliver this talk on speech enhancement technique for automation, and its demonstration that you have shown and responded to the queries of the participants. I would like to thank you from my side as well as from the side of Dr. Wajid and from Department of Electronics Engineering as a whole, that you have been kind enough to accept our invitation and deliver this talk, which was very interesting. And we would thank you, ma'am, very much.
It's a pleasure. Thank you so much, sir.
Thank you very much, ma'am. So we'll be contacting you after 1 week of this FDP for all the formalities.
Sure, sure. Anytime, anytime. Thank you so much.
Thank you. Thank you. Okay. 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 Goodbye. Goodbye.
Goodbye. Bye.